An ANOVA table is used to organize the computations involved in calculating the F-test statistic. Following is the ANOVA table for the previous example regarding the consumption of calcium. So what I have right here is just an ANOVA table, which is, again, an organization of the information that we just found in our previous calculations. So for example, what I've got here in the ANOVA table is I have the source of variation. So is it variation due to treatment or is it the variation due to error? So the variation due to treatment is the 44,694.043. And that is what we found right here by hand. So I've just organized that there. There were 2 degrees of freedom due to treatment, so I've put that right there. And the mean squares due to treatment is right here, the 22,347.0215. I rounded to 022 here, but that is that information. For the error, the sum of the squares due to error, that is the 30,084.796. The degrees of freedom due to error, that is the 21, that's the n minus k. And then if I take that divided by 21, that is the 1432.609 that we have here. And then if I take the mean squares due to treatment and divide by the mean square due to error, that gives me the F statistic. So I've just organized that information into this ANOVA table. This number right here, the 74,738, that is the total. And so that's just these 2 added up. So the total sum of squares is going to be these 2 added up. And the total degrees of freedom is going to be these 2 added up. We don't do that for the mean squares or anything else. Now, when we do ANOVAs using technology, usually the technology is going to give us our information in the form of an ANOVA table. So that's why I've addressed that here. Now, concluding a one-way ANOVA test. Because the F-test statistic is the ratio of the mean squares due to treatment to the mean squares due to error, ANOVA tests are always going to be right-tailed tests. So we're always going to have right-tailed tests when we're dealing with an ANOVA test. To conduct an ANOVA test using the classical approach, we're going to compare the F-test statistic to the critical value. So the F-test statistic, that's F naught that we've calculated, to a critical value, F sub alpha, that we're going to find in table 9. The critical value, F sub alpha, is the F value whose area in the right tail is alpha with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator. To conduct an ANOVA test using the p-value approach, compare the p-value to the level of significance alpha. The p-value is the area beneath the F curve with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator to the right of the F-test statistic. And then our decisions, like normal when we do a hypothesis test. The classical approach, since this is a right-tailed test, if the F-test statistic is bigger than the critical value, we're going to reject the null hypothesis. If we use the p-value approach, if the p-value is smaller than alpha, then we're going to reject the null hypothesis. So example, conclude the ANOVA test from the previous example regarding consumption of calcium for children who exclusively use lean meats, mixed meats, or higher fat meats. So we're going to conclude our ANOVA test for the calcium consumption problem, and then we're going to draw box plots of the 3 treatment levels to support the conclusion of the ANOVA test. So if I use the classical approach, for the ANOVA test, then I need to find a critical value. So here we have the F distribution table from the appendix of our book, pages A-16 through A-19 gives us different values. And Here we have the shape of an F distribution. So it is also skewed right, sort of like the chi-square distribution is generally a skewed right distribution. The specific shape is affected by both the degrees of freedom in the numerator, which is the degrees of freedom due to treatment, and the degrees of freedom in the denominator, which is the degrees of freedom due to error. So we have to look this up sort of two different ways, dealing both with the degrees of freedom in the numerator and the degrees of freedom in the denominator. So if I'm going to use the classical approach, then I need to find my critical value. And I didn't say in this problem what to use for the level of significance, but let's use alpha equals 0.05 for our level of significance. So this area here in the right tail is going to be alpha equals 0.05. And in this particular case, again, remember that our degrees of freedom due to treatment is 2, and our degrees of freedom due to error is 21. So our degrees of freedom due to treatment is 2. Our degrees of freedom due to error is 21. So I need to figure out what that critical value is here. That's going to be our F sub alpha. That's going to separate the rejection area from the non-rejection area. So here's how this works. So I'm going to, again, pull in my table, and I'm going to have 2 degrees of freedom in the numerator. Now, how do I know what's the difference between the numerator and the denominator? Well, here's how I think about it. If you think about your F calculation, the mean square due to treatment is in the numerator, and the mean square due to error is in the denominator. So the degrees of freedom due to treatment is going to be in the numerator, and the degrees of freedom due to error is going to be in the denominator. So we have 2 degrees of freedom in the numerator, and we have 21 degrees of freedom in the denominator. So 2 degrees of freedom in the numerator, I'm going to go to that, and I need to find 21 degrees of freedom in the denominator. Well, that doesn't fit on the first page of this table. It's also not on the second page of this table. If I go to the third page of this table, now my degrees of freedom in the denominator go from 9, 10, 12, 15, 20, 25, and so on. I don't really have 21 degrees of freedom in the denominator, so I'm going to have to use the closest thing to it, which is 20 degrees of freedom in the denominator. So that's going to give me a slight little bit of error. So I have 2 degrees of freedom in the numerator. I have 20 degrees of freedom in the denominator. Again, really 21, but I have to use 20 in my table because it's a limited table. Now, if you look at this block right here in my table, so this would be the critical value if alpha, the area in the right tail, is 0.10. This is the critical value if alpha is 0.05, 0.025, 0.01, 0.001. So in our case, I said, let's use alpha equals 0.05. So our critical value is going to be 3.49. So 3.49 is our critical value, approximately. Now, again, that's going to be off just a little bit because of the fact that we have 21 degrees of freedom in the denominator instead of 20. But it's not going to be off so much that we're going to get an incorrect conclusion. Now, again, if I'm using the classical approach, remember our F test statistic is 15.599. So if F naught is equal to 15.599, that's going to be way over here to the right. So I'm going to reject the null hypothesis. If I reject the null hypothesis, going back a couple of pages, remember the null hypothesis was that all 3 means are equal. So I'm rejecting that. So my conclusion is that at least one mean is different. So this is my conclusion. Now, if I use the p-value approach, the p-value is going to be the area to the right of the f-test statistic. So our f-test statistic is 15.599, and I need the area to the right of that. And again, I have the degrees of freedom due to treatment is 2, and I have the degrees of freedom due to error, that is 21. This is the numerator, this is the denominator. Now, I can't really find the p-value using the table, so we'll generally not use the table for finding the p-value, but we do have command on the calculator, and we have command or a calculator in StatCrunch that can find this p-value for us. And so if I go to distributions, we've been here lots of times. If you look on my calculator, it's options 9 and 10. I have FPDF and I have FCDF. Well, the FPDF command is if I want to draw an F distribution, like the graph of an F distribution, which we're not going to do in this class. The FCDF is like the normal CDF or the TCDF or the chi-square CDF commands that we've used. That's going to find the area beneath an F curve for me. So here's how that works. When I select that, I need my lower bound, which in this case is 15.599. I need an upper bound, which I don't really have one, so I'm going to use a big positive number. Again, that works like the normal CDF, the TCDF, the chi-square CDF commands that we've used before. The degrees of freedom in the numerator is 2. The degrees of freedom in the denominator is 21, and I'm going to paste that. Now, when I paste that, I get this command on my calculator. And if you have an older calculator, when you go to the FCDF command, you have to type it in. You don't get the window like I got on my calculator if you have an older one. So the command as a general rule is going to be FCDF. You're going to have the lower bound. You're going to have the upper bound. You're going to put in the degrees of freedom for the numerator and the degrees of freedom for the denominator. That's the general command that we have here. So in this case, that p-value is FCDF. We're getting it from 15.599 to a big positive number with 2 degrees of freedom in the numerator, 21 degrees of freedom in the denominator. When I hit enter, that is 7.0459 times 10 to the negative 5 power. That's scientific notation. So this would really be 0.000070459. And if I round that to 4 places like we normally do, that would be 0.0001. So that's a very small p-value. So because the p-value is less than alpha, that's less than 0.05, for example. So because the p-value is less than alpha, we reject the null hypothesis. So our conclusion, same conclusion. At least one of the means is different. So now we're back here at StatCrunch again. Part B, we're supposed to draw box plots of the 3 treatment levels to support the conclusion of your ANOVA test. So I have our 3 treatment levels here. I'm going to go to graph, and I'm going to create 3 box plots. So I'm going to go to box plot, and I'm going to select our 3 groups: lean meats, mixed meats, higher fat meats. I'm going to use fences to identify any outliers, and I'm going to draw the box plots horizontally. If I compute, here are the 3 box plots. So this box plot is representing the higher fat meat data. This is the mixed meats data, and this is the lean meats data. Now, we just concluded that at least one of the means is different from the others. Does this box plot sort of support that? Well, if you look at the box plot, like let's start with lean meats, we got a median over here close to 800. And then we have, if you look at the mixed meats, we have a median close to 900, actually above 900. I can actually see what it is. It's 902 versus this one's 800.65. So now the median and the mean aren't the same thing, obviously, but it certainly looks like, as a general rule, this entire box plot's pretty far to the right of the lean meat box plot. And then if you look at the higher fat meats, it's kind of more in the middle. But this certainly does indicate maybe that there are differences in the three groups. If these were all the same, then these box plots would overlap a lot more. So it would be like if the lean meats was here and then the mixed meats was here and the higher fat meats was here and they were overlapping a bunch, that would indicate more like they're all the same. But in this case, we've concluded that at least one of the means is different from the other, and it looks like maybe like mixed meats is definitely different from lean meats. So we've drawn the box plot, and we can see this does support our conclusion that at least one of the means is different. I'm not going to draw those box plots by hand, but we did see in StatCrunch that it does appear that at least one of the means is probably different from the others. Now, on the next page of the notes here, I have included steps on how we can do ANOVA tests using both our calculator and StatCrunch. So, example, using both a TI calculator and StatCrunch, repeat the ANOVA test from the previous examples regarding consumption of calcium. So the same data, if I bring in my calculator, and again, I've included steps here. If I go to Stat and Edit, prior to starting this video, I entered the 3 sets of data into the lists of my calculator. So in list 1, I have the lean meats data, list 2, I have the mixed meats data, and list 3, I have the higher fat meats data. So with those data in the lists of my calculator, I'm going to go back to the home screen. And if I want to conduct an ANOVA test, I'm going to go to Stat and Tests, and I'm going to scroll down to the bottom of this list, and I have, it's the very last one. On my calculator, it's option H, ANOVA. Now, here's how that works. I select ANOVA, and I get this command on the screen of the calculator, on the home screen. So all I'm going to do is tell the calculator what lists have the data that I'm comparing. So I have my lean meats data in list 1, so I'm going to put L1, comma. I have the mixed meats data in list 2, so L2, comma, and I have the high fat meats data in list 3. And then I'm going to close the parenthesis because those are the only 3 things that I'm comparing. If I was comparing 4 sets of data, then I would also have to have data like in list 4, and I would put comma L4 and so on. If I hit enter, I get first and foremost up here at the top, the F test statistic. So the F test statistic is going to be 15.599 if I round to 3 places. So F naught equals 15.599. That is the same calculation we got by hand. I get the p-value is 7.046 times 10 to the negative 5. And if I write that in standard form, that's 0.00007046, which would round to 0.0001, which is the same answer we got by hand. Now, again, if you compare the specifics, you might see a little bit of discrepancy because I had rounded a little bit. So those are really the only 2 things I need in order to do my test. Like, for example, if I find the p-value, Well, the p-value is 0.0001. That's less than 0.05, so I reject the null hypothesis. Also, the calculator gives us information for like the sum of the squares due to treatment, the mean squares due to treatment, and so on. So if you take a look, for example, now the calculator calls it factor instead of treatment, but we have the degrees of freedom due to treatment is 2, which we found. We have the sum of the squares due to treatment, 44,694.04333. Now, those are the same things that we found right here by hand. So there's the sum of the squares due to treatment. Notice we got the exact same answer. And the mean squares due to treatment, 22,347.021. Now we got 5 because of rounding. They got 6, 7 back here. But that's pretty darn close, right? And again, I got a little bit of error because I had rounded. But the point is, that's the mean squares due to treatment, the sum of the squares due to treatment, and that's the degrees of freedom due to treatment. The calculator calls it factor. And then it has error. So there's the degrees of freedom due to error, 21, the same thing we got by hand. The sum of the squares due to error, so 30,084.796. And then the mean squares due to error, 1432.6093. Again, we agree with all of those by hand calculations. So basically, the calculator gives you all of the information that goes in an ANOVA table. So again, we can do this by using the calculator. In StatCrunch, I have the data here. And so if I want to do an ANOVA test, I can go to Stat and logically, looky here, there's ANOVA. So I select ANOVA. When I select ANOVA, I'm going to choose a one-way ANOVA. That's what we're doing. There's also something called a two-way ANOVA that we don't cover in this course. So we won't be doing a two-way ANOVA. So you're always going to select one-way ANOVA. Select the columns that have the data in it. So in this case, lean meats, mixed meats, higher fat meats. And that's really all I need to do at this point. If I say compute, what I get here is an ANOVA table. I get lots of information, like this is all the individual information for the 3 groups. The sample size, for example, for lean meats is 8. The mean is 794.7625. The standard deviation, 33.9659, blah, blah, blah. So it gives me all the individual statistics, but what I really want for the ANOVA test is right here. So for the columns, now StatCrunch calls it columns, but this is the treatment. So the first row is the treatment. So the degrees of freedom is 2. The sum of the squares due to treatment, 44,694.043. The mean squares due to treatment, 22,347.022. All of that agrees with what we got by hand. The error, 21 degrees of freedom due to error. Sum of the squares due to error, 30,084.796. And the mean squares due to error, 1432.6093. And then it gives the totals, like what we talked about by hand. If I just add the degrees of freedom here, the 2 and the 21 is 23. This plus this gives me the 74. And then the F statistic is 15.599 if I round to 3 places, the same thing that we got by hand. And the p-value in this case is smaller than 0.0001. So it's even less than 0.0001 is what StatCrunch is saying. All of that agrees with what we got both on the calculator and by hand. So then I just have to conclude the test, either by using the classical approach or the p-value approach. I also want to point out that on StatCrunch, if I go to Stat and Calculators, I have an F distribution calculator right here. So I have degrees of freedom in the numerator and degrees of freedom in the denominator here. So if I have 2 degrees of freedom in the numerator and 21 degrees of freedom in the denominator, and if the area in the right tail, so I change that to greater than, is 0.05 and compute, that gives me the critical value. So the critical value would be 3.467 for this test. So I could use this F calculator if I wanted to in order to find the critical value instead of the table if I want to use the classical approach. Although typically we won't want to use the classical approach. Typically we will want to use the p-value approach. It's much simpler.